Γεια σας. Ο Γρηγόρης μου είπε να κάνω την introduction στα ελληνικά, αλλά μάλλον θα κάνω πολλά λάθη, γι' αυτό θα κάνω switch στα αγγλικά. Θα ήθελα να ήμουν στην Αθήνα σήμερα, αλλά δυστυχώς δεν μπορούσα. So hello everyone, my name is Najwa Aaraj. I'm the Chief Researcher of the Cryptography Research Center at the Technology Innovation Institute in Abu Dhabi, the United Arab Emirates. I'm also heading on an acting basis the Autonomous Robotics Center at Research Center at the Institute. I would like to thank Greg and the organizing committee for having me here. Today, my talk would be on the impact of quantum computers and machine learning on cryptography and cryptographic systems. Maybe this topic is not mainstream for B-Sides, so I do hope that you enjoy the presentation. So as I said, the talk today is about what would quantum computers and machine learning do to cryptography and cryptographic systems. I guess all of you are familiar with the concept of cryptography, which, to put it simply, it's a set of mathematical algorithms or operations that are conducted on plain text between two parties in order to ensure confidentiality, integrity, and authentication of data, and providing other properties like non-repudiation, for example. There are two types of cryptographic systems. We have the symmetric cryptography systems, where the sender and the recipient, or basically the two involved parties, they share a secret key, either through pre-sharing it or establishing it through an algorithms like Diffie-Hellman, for example. Then the data is encrypted and decrypted using this shared secret key. And we also have the asymmetric crypto, or what we know today as the public key cryptography, where each of the parties, what we call here Alice and Bob, each one of them has a pair of a public key and a private key. So whenever I want to send an encrypted information to the recipient, I use the public key of that recipient to encrypt the data, and that recipient, obviously after authenticating him or her, and that recipient being the only holder of the private key would be able to decrypt the information. You're familiar with the components of what we call today the ensemble of algorithms that we call the symmetric crypto. So we have block ciphers, all of you know about AES. We have MACs, we have hash functions, pseudo-random number generators, key derivation functions or KDF, stream ciphers, authenticated encryption, and memory heart functions. You're all familiar with RSA and ECC, which are classified under the asymmetric cryptography, cryptographic systems, and the concepts of key exchange, which we do using Diffie-Hellman or EC Diffie-Hellman, and also with the concept of digital signatures, DSA or ECDSA. And the same way we have cryptography, the design and the implementation and the security analysis of cryptographic systems. We also have what we call the cryptanalysis. We have the theoretical cryptanalysis and the algorithmic attacks, like the chosen plaintext attack, where basically the attacker sends his own plaintext to the oracle and then receives the ciphertext back. And then we also have the chosen ciphertext attacks. We have cryptanalytic attacks against implementations of cryptographic systems, and the most common ones are side channel analysis. So either timing attacks, cache attacks, memory attacks. We also have power attacks, both simple and differential power attacks, EM attacks, also both simple and differential EM attacks, and others. And also we have fault injection attacks. So these are the attacks or the cryptanalytic attacks that we know today in the classical sense or the conventional sense. And today we have another threat to cryptography, which is basically the quantum computers. So focusing on asymmetric cryptography, both RSA and ECC, they are based on mathematically hard problems, where even the most powerful computers and supercomputers that we have today would take years and centuries in order to be able to break those mathematical problems. So RSA relies on integer factorization or prime factorization, and the hard problem on which ECC or elliptic curve cryptography relies today is discrete logarithms. So as I said, today the most powerful supercomputers cannot unravel the puzzle around these two hard problems. However, with the advent of quantum computers, and quantum computers is a reality, we hear, about breakthroughs every day, regardless of the technology, whether it is a superconducting technology, whether it is an ion trapping technology, etc. They're becoming a reality. And I guess most of you would have heard, especially as of late 2019, about quantum supremacy and the potential ability of quantum computers to solve problems that classical and conventional computers practically cannot solve. And from a crypto sense, I know two quantum algorithms. We have the Shor's polynomial time quantum algorithm, which can factor integers and compute discrete logarithms efficiently. So what this means, based on what I said before, because we have this polynomial time quantum algorithms, the security of public key cryptographic algorithms basically is gone to zero. So it's broken. And we have Grover algorithm, or what we call Grover search, which can be used today, which basically reduces the security level of symmetric algorithms by half. Recent studies said that basically for encountering the threat, the key size of symmetric crypto algorithms would go by 70%, not 100%. But in any case, what I'm trying to say here is that the symmetric algorithms are impacted because of Grover search. It's not as much of a priority as it is for public key crypto, but still there is an impact through this quantum algorithm. So given this, there are differing point of views on how to prevent the threat of quantum computers against public key crypto systems. So as you can imagine, the physicists would say, use quantum technologies to fight quantum technologies. In other sense, use what we call today the quantum key distribution systems in order to fight the threat of quantum computers to cryptographic systems. And this is what we call today the quantum cryptography field. And cryptographers say, base your crypto on math or mathematical problems, hard problems that quantum computers cannot break. And this is the whole concept behind quantum resistant or post-quantum cryptography. So post-quantum cryptography, basically, it consists of algorithms that run efficiently on classical computers, but are hard to break even with quantum computers. So in other sense, these are different, they use different mathematical problems than integer factorization or discrete logarithms. So there is obviously a need to revamp or revise the standard for public key cryptography. In other words, we need new post-quantum algorithms. In early 2016, NIST announced a plan to select and standardize post-quantum algorithms for public key encryption, for key establishment, or what we call in the post-quantum world, key encapsulation mechanisms, and for digital signatures. The deadline of submissions was in November 2017. The competition is still ongoing. It's at its round 3. Finalists have been announced, and most likely, and actually I think it's a fact that there is a 4th round and a call, especially that's happening most likely towards the end of this year for candidates, especially for digital signatures. So basically, these are the updates as of last year, 22nd of July. You can see that there are multiple candidates for post-quantum cryptography, both on the public key encryption, key encapsulation, and signatures. There are multiple hard problems based on which post-quantum algorithms are based. Without going into too much detail, we have what we call today the lattice-based cryptography. Usually there are strong candidates for encryption, signatures, and key encapsulation or key exchange. They are based on what we call the SIS and the LWE problems. These are the hard problems based on which they are based. So basically, they are the shortest integer solution and the learning with errors problems. We also have code-based cryptography, which is based on coding theory, still secure parameters there are still secure parameters for Macalist's crypto system, and this is quite an old crypto system that was suggested in the 1978. They have the key size is large, so they have bigger keys, and they are attractive mainly for encryption. We also have post-quantum cryptographic schemes these are the multivariate polynomial cryptographic schemes, and they are based on solving systems of multivariate polynomials. I guess multiple schemes that have been proposed have been broken, but signatures based on multivariate polynomials still have some potential. We have also post-quantum schemes that are based on symmetric primitives, and in particular hash functions. So because they are based on hash functions, their post-quantum security is quite well understood. And this is where I quote, basically, I mentioned the hash-based signatures. And also we have cryptographic schemes. I think here I bundled it under others, which is the isogeny. It uses isogenies, or it's basically based on isogeny problem of super singular curves. Basically, there were few proposals for key exchange. It's an isogeny Diffie-Hellman for key exchange. It was proposed. The key sizes are smaller, but we still have performance issues for those crypto systems. And maybe this is why you see them selected as alternative here. So to sum it up, there are finalists across all these schemes: lattices, codes, multivariates, hash-based signatures. There are few that were selected across all of them as finalists in the post-quantum competition, and there are also few that were selected either as finalists or alternate candidates for key encapsulation mechanisms and public key encryption. So you see that we might be heading already towards new standards for post-quantum crypto, but as I said before, the competition is most likely going to continue with the fourth round, especially for the calling for submission of new digital signature schemes. Now, the standardization efforts are great, but as researchers in general, or security researchers or security practitioners, I'm sure the first question that comes to mind is that how are we going to transition from current cryptographic systems, which in most cases they are either non-existing, which actually it might make it a bit easier to do that, or there are legacy systems that rely on very old implementations and old schemes with reduced key sizes and bit level security. And obviously we will face lots of challenges and complexities in this roadmap to transition from whatever we have deployed today in terms of data at rest security cryptographic systems and secure communication solutions. So how are we going to move from whatever exists today in the classical sense to post-quantum alternatives? And here you see lots of efforts that are happening to introduce what we call a hybrid approach, or basically hybrid schemes. And it is very crucial for organizations to recommend, to deploy, and researchers or practitioners to recommend agile crypto systems. So in the hybrid sense, basically the evolution towards post-quantum crypto will be using a hybrid approach between classical standardized algorithms combined with new post-quantum algorithms. So for example, for key exchange or for key establishment, we would use an extension between the key exchange algorithms as we know them today and key encapsulation mechanisms. And also there should be a hybrid approach, because today we still don't have standardized primitives, a hybrid approach between post-quantum and post-quantum. So I guess this is it for the post-quantum talk, and I see myself that I already bypassed 16 minutes, and I have instructions to only stick to 20 minutes. So I will go very quickly through the second part of this talk, and it is basically the application of, or basically the intersection of machine learning and cryptography. So cryptography, based on what I've been saying and what you guys know, it seems like a complex problem, mathematics, constructions, etc. So the question comes, how can machine learning contribute to any crypto field? So if we take a step back and put it quite simply, machine learning learns from training data. It makes predictions on new data through a model built, through the machine learning model that we built. Does this help tackle all crypto problems? Well, not quite. We have the NP-hard or the intractable problems that are not a candidate because implied operations and complexity classes are not probabilistically and approximately learnable. As I said, it takes a quantum computer capable of running Shor algorithm in order to achieve that. But what this means is that what we can do is define problems or models probabilistically and approximately. So for each plain text X with a distribution of V and a mapping function C, we can learn a model which maps X to a value, and it maps actually X to a value, and that value would agree with the ciphertext with a very high probability. So basically, I managed to approximate a cryptographic problem with a machine learning model, and the output of this machine learning model agrees with the output of the crypto system or the ciphertext with a very high probability. So what I'm trying to say here, I think I went too complex here, but what this means to cryptography, and this is today, actually, this is one of the main research problems that we are working on CII, and this is fairly leading edge, is that how can machine learning, how can I use this, what I just mentioned, for machine learning to help with cryptanalysis? And you know, as I mentioned before, cryptanalysis is the opposite of cryptography. So it is concerned with recovering a plain text from the ciphertext, either by recovering a key or by finding a relationship between the ciphertext and the plain text. You know, cryptanalysis is just not one text, okay, not one test that the researcher does and that's it. It's a set of tests between linear, algebraic, meet in the middle attacks, etc. And the question is, how can machine learning help speed up and automate cryptanalysis? Obviously, this can only be beneficial if we find algorithms with a space complexity that grows logarithmically to the size of the feeding data. And one cryptanalysis way which we are exploring today is to help find differential characteristics and estimate states inside the cipher between plain text and ciphertext. And the better the quality of this nonlinear relationship, the harder it is to find this model, and the stronger the ciphertext will be. The ciphertext will look closer to a random question. Now, if this relationship between the clear text, what you see here as P1, and the ciphertext is not as good, a machine learning model can be found. So how does this help? Basically, the model helps analyze crypto algorithms in a faster and a more automated way. It helps basically do more basically faster and automated analysis for differential attacks over cryptographic implementation. So both from design, security, and the implementation, this model help decipher or break cryptographic algorithms. And then by doing so, it helps you because it highlights to you the security properties. It can help increase the security bounds in cipher designs. I have many more slides, but I guess I'm running out of time. The second area where machine learning can help in the cryptographic field is also, it's a cryptanalytic area, but it can help with implementation-based cryptanalysis. So, and this is actually machine learning can be quite powerful here. So to explain a bit better, one of the most common ways to recover keys and subsequently clear text today is side channel analysis. And this is, typically it requires physical access, and it requires getting signals or traces from a specific crypto algorithm. Obviously, you have the signal processing part in order to pinpoint exactly where the crypto algorithm is running. But machine learning is one actually of, it's quite powerful to be a help or to be of assistance in side channel analysis. So today, basically, I'm not going to go into the detail of side channel analysis, but supervised learning, especially MLP and CNNs, can help quite a bit for profiling and stochastic and template attacks when it comes to side channel attacks. We can use machine learning in side channel attacks for classification, clustering, feature engineering, and pre-processing. CNNs in particular are quite basically convolutional neural networks. They are in particular quite useful for this because they learn abstract representation with at each level or at each layer of the network, so they work best. This is, this area of using machine learning in side channel analysis is still fairly new. However, it is quite promising, and it is to be thoroughly tested, even in the presence of masking, thresholding, and other countermeasures. Machine learning can help with deploying security on energy constrained devices, and this is one of the main areas that I'm personally quite active in the research of. And here the idea, without going into the detail of that, here the idea is that I use quantized neural networks or prone neural networks on embedded devices. Because today ANNs have found really good success in big data applications. There is a quite significant interest of using artificial neural networks for medium and small data applications that can be run on embedded systems, sensors, IoT devices, energy constrained devices in general. However, lots of efforts that have been done to migrate those ANNs to such devices has entailed a big loss function, or a significant loss to the classification accuracy. So here, what the research here is about pruning neural networks and to be able to run efficiently with an acceptable accuracy on embedded devices. And basically what this does is that by having those the prone neural networks, and that are fairly energy efficient, and then that can run on the energy on the end device or the edge device, you can have lots of computational power that is saved by having on-device intelligence, and basically not using this and then saving power and not using this power for constant communication between an edge device and the cloud. So you save on the communication energy, and you would be able to run further, you would be able to do inference on device, not needing an external communication for doing the intelligence on a cloud or an external server. And then by saving this energy, you would be able to run further cryptographic functions or cryptographic protocols or other security mechanisms on the edge device itself. And then finally, machine learning can be quite useful in the context of confidential computing, privacy preserving schemes in general, fully homomorphic encryption, etc. Unfortunately, I don't have time to go through it, but basically the idea here is that by using machine learning. So I execute a machine learning algorithm to a computing service while retaining confidentiality of the data. So basically using homomorphic encryption schemes, I keep my data encrypted and then I do operations on my encrypted data. So I can manipulate the data. I can do any complex operation of the data without decrypting it. So for example, a cloud service can perform several tasks without exposing this private information. However, today, this is still FHE, or fully homomorphic encryption, is still considered as the holy grail of cryptography. It's still quite slow. So as you can imagine, for real-time operations, that's quite a problem. However, there's a lot of research efforts that are going into FHE, into hard, and also doing software optimization and developing hardware accelerators as well. There is a very clear use case for federated learning, and I guess I will stop here. I would be very happy to take questions online, and hopefully on the day I will be able to be online as well to take your questions. Thank you very much once again, and I do hope that you enjoy the talk when you listen to it. Bye-bye.